Okay, so we are looking at inheritance hierarchies. Which are represented by a graph which is made up of vertices and edges. Now, edges are of two kinds, positive, for example a dot x, which would be x a, or they can be negative, a dot not x, which would have a slash across the edge that we draw essentially. Now, allowed paths are of two kinds. Again they are positive and negative. So, positive path would say a dot x 1 dot x 2 dot x n dot some property v, let us say, where every edge is positive essentially. Negative paths are of the kind a dot x 1 dot x 2 dot x n dot not v. So, only last edge can be negative. Now, the reason for that is it does not really make sense to have a path which has more than one negative edge. So, for example, if I say that for example, Nemo is not a mammal. Okay. So, I have a network in which I have mammals, then I am saying Nemo is not a mammal, and then I have another thing which says that let us say fish essentially. So, I have a knowledge base in which say mammals are not fish, and I am saying Nemo is not mammal essentially, or I can say mammals are not birds. So, these are paths which have length more than, which have more than one negative edge. So, if Nemo is not a mammal, and how does it matter whether mammals are birds or not birds, or mammals are fish or not fish, and so on and so forth. Nemo is not a mammal. So, whatever you say about mammals is irrelevant to Nemo essentially. So, because of that reason such paths are not allowed essentially. So, you cannot have more than one negative edge in a path. So, only one negative edge, and such a path is called a negative path essentially in a one network. So, we say that a path supports a conclusion. So, for a positive path, in this example we can say that it supports that A is a V, so let me change that V to W just to distinguish between the two paths, and the second conclusion is A is not a W. This is in general what paths are used for essentially. So, a path supports a conclusion, that if there is a positive path going up to some label, then we can say that A, the individual that we are interested in is has that property or is or belongs to that class or whatever that may be, or if it is a negative path, then we know that it supports a negative conclusion about that path essentially. Now, the only question we want to ask is that in the face of ambiguous networks in which there are conflicting conclusions that you can draw, which is the one that you would like to believe in essentially. So, for that we have a notion of admissible paths, which are allowed or which can be believed in, or you might say which are credulous. So, we say that a conclusion A V is supported if there is a positive path A dot x 1 dot x 2 x n dot v, which is admissible. I will define admissible in a moment. In a similar fashion, we can say that A dot not W is supported if there is a negative path A dot x 1 dot x 2 dot x n dot not W. Now, a path is admissible if every edge in the path is admissible. So, there is something which I have not stated here. This notion of admissibility is with respect to A. So, admissible with respect to E. All notions of admissibility are with respect to one particular individual. Obviously. So, if you are talking about Clyde, then as far as Clyde is concerned, you should be able to believe that Clyde is white and so on essentially, or that elephants are white or grey elephants are white or whatever you come to this essentially. So, now we are talking about an edge let us say x n dot v or x n dot not w. They are treated in a similar fashion, whether it is a negative edge or a positive edge. If so every time actually we must say with respect to A, if there is a positive path A x 1 x 2 x n, which is or which has the following properties. So, before I state the properties, we have seen that we have sort of handled the negative paths from now, whether it is a negative path or whether it is a positive path. In our notation here, there must be a positive path going from A to x n essentially. It is only the last edge x n to v or x n to not w which is positive or negative. Otherwise, they both must have a positive path leading up to x n, which must be admissible essentially. So, this treatment of course, is applies to in general, except that you must keep in mind that the negative edge can only be at the end of a path essentially and nowhere else essentially. So, let me state that admissibility of an edge x n dot v, we said that if there is a positive path, so again with respect to A, okay, in which each edge is admissible with respect to A. So, every edge must be admissible by the same recursive definition. No node x I on the path must preempt the edge x n dot v. And what do we mean by this? There should be no edge or the following edge is not present, x I dot not v should not belong to the so, I am not use this notation. This notation basically says that is the inheritance hierarchy. We will just give it a name tau. So, we are saying that on this path which is going from A to x 1 to x 2 x I x n v. So, we are talking about the admissibility of this edge x n to v, which of course, will apply to any edge in general. We are saying that every edge in this positive path from A up to x n must be admissible, and there must not be an edge like this. No node must preempt that thing, which means that an edge like this must not be present in the this thing. If this was a negative edge x n dot not w, then you would just replace this with x I dot w. So, the treatment is identical, whether it is the last edge is positive or negative, it does not really depend upon that. Basically, there must not be an opposing edge coming from some intermediate edge essentially. And the third property is no edge in the path must be redundant. We saw that when we introduced a new edge which said that Clyde is an elephant, it basically messed up this thing. So, essentially what this condition is saying that such edges which are essentially redundant edges are not allowed essentially. And a redundant edge is as follows. So, in general an edge x y in a path is redundant with respect to A if there is a path x dot x 1 dot x 2 dot x n dot y. In fact, we should say a positive path, because the only negative edge can only be in the last of any meaningful path. So, we say that an edge x y is redundant if there is a positive path. So, if there is a positive path going from x to x 1 to x 2 to x 3 to y, let us say there are only these things, then this edge is redundant. There are certain conditions here, and there is no node C such that C dot x C dot not x I or C dot not y belongs to our network. Which means that if I have a node called C like this, and it is giving a negative edge to this, or it is giving a negative edge to y, then x y is not redundant. X y is redundant is that there is no such thing which is spoiling the path which the longer path which is going from x to y. X y is redundant only if there is no such C essentially, which means you can just throw away the redundant path and you would still have the same inheritance hierarchy essentially. So, if we go back to our example now, which was about elephants. So, gray, I will just write elephant here, then royal elephant here, then fat royal elephant here, and Clyde here, and then we had this, and then we had this. So, essentially there are 3 paths in this example. So, this is the example. The path which goes from Clyde to fat royal elephant to royal elephant to elephant to gray. Is this admissible? So, we are looking at this middle path in this network. This path is not admissible because there exists a node Royal elephant on the path which preempts that node that edge E dot gray. So, the answer is no. R E dot not gray preempts E dot gray, and in this path this edge is part of this path essentially, and this is being preempted by some node which is in the path, which is this node R E, and therefore, the answer to this is no essentially. This path which is a short path Clyde dot elephant dot gray, is this admissible? The answer is again no, because Clyde dot elephant is redundant. Clyde dot elephant is redundant because there is a path from Clyde to fat Royal elephant, from fat Royal elephant to Royal elephant, from Royal elephant to elephant, and there is no C that we talked about, which will upset this relationship in some sense. So, which means we cannot count this path which goes from Clyde to elephant to gray as an admissible path essentially, because it an admissible path cannot have a redundant edge. So, there are these two examples, the one which is the straight example which says that Clyde to fat Royal elephant to Royal elephant to gray, that is not admissible because the topmost edge which says elephants are gray is preempted by Royal elephants are gray, which is on the path. The path which goes via Clyde to elephant to gray is not admissible, and the third path that remains, which is Clyde to fat Royal elephant to Royal elephant to not gray, is admissible by the definition. So, we have a definition of admissibility which is kind of consistent with what we intuitively feel about this knowledge base. This knowledge base has said that Clyde is a fat Royal elephant, fat Royal elephants are Royal elephants are elephants, elephants are gray. You might say, but Royal elephants are not gray and Clyde is the elephant. Given all this information, what we would really intuitively believe is that Clyde is not gray essentially, because in this case the specificity criteria about Royal elephants applies. But the important part is that this definition of admissibility that we have agrees with our intuition about what we want to believe exactly. Okay, so, we have this definition of admissibility which allows us to say that which paths are allowed or not allowed essentially. So, finally, we want to say that given an inheritance hierarchy, what are the credulous beliefs we can hold about an individual essentially. We will address that in the next class. So, I will stop here with the definition of admissibility. In the next class, we will finally talk about, given a network, what can we believe about an individual essentially. Because we remember that there can be ambiguous paths, there are paths which are inherently ambiguous essentially. For example, there may be two paths which are of equal length, one of them says that penguins are birds and birds can fly, the other one says penguins are aquatic birds and aquatic birds cannot fly, they are both of length 2. So, how do we believe which one essentially, or which is an alternate set of things to believe essentially. So, we will look at that in the next lecture.